This is the tutorial for neutron CW powder data, yttrium iron, and aluminum garnet. In this tutorial, you will refine the structure of yttrium iron and aluminum garnet using constant wavelength neutron data. The structure is cubic with 4 different atomic sites, 2 of which are occupied by both iron and aluminum. The data was taken on the D1A powder diffractometer at the ILL Grenoble, France, using 1.909 angstrom wavelength neutrons. If you have not done so already, start GSAS2. Step 1 involves reading the data file. At the top of the window, go to Import Powder Data from GSAS File to read the data file into GSAS2. This read option is set to read any of the powder data formats except neutron TOF time map files. They are defined for GSAS with the angles in centigrees. Find the file directory, CWNeutron, and go to the data file to find the file. Select the garnet.raw data file in the first dialog box and press Open. In the window asking, "Is this the file you want?" click Yes. Then select the inst_d1a.prm instrument parameter file in the new dialog box. Click Open. At this point, the left side of the GSAS2 data window will have several entries. This column is called the GSAS2 data tree. The next step is to create the phase. Go to Data, Add Phase to begin the creation of the new phase for this garnet. Enter a phase name in the dialog box. We assumed the name Garnet. The default phase information will immediately be displayed. Go to the General tab. Note that the phase type is set to nuclear. The other options, like magnetic or faulted, can be used for other structural problems. Click on the Space Group box and enter the space group in the new window. Capital I, space A, space 3, space D. Remember that the spaces between axial fields are required in GSAS2. Click OK. In the new window, the space group information will appear. Press OK to exit. Notice that your General tab display will change. In the unit cell, A equals box, enter 12.19 and press Enter. This is the lattice parameter for Garnet. The cell volume is revised and changed on the screen. Click on the Data tab within the Garnet phase, and at the top of the window, select Edit Phase, Add Powder Histograms. A Use Data window will appear. Select the one choice powder garnet.raw bank 1 and press OK. This window is home of the parameters that are both phase and data set dependent. These include phase fraction, crystallite size, mu strain, and preferred orientation. The next step involves inserting the atoms. Click on the Atoms tab within the Garnet phase. This is where you will insert the atoms for the Garnet structure. At the top of the window, go to Edit Atoms, Append Atom. Do this a total of 6 times to create the default set of atom places in the table. For the atom in row 0, double-click on the H in the Type column. A periodic table will appear. Select Y from the pull-down menu. For the coordinates, change X to 0.125, Y will stay at 0, and change Z to 0.25. Repeat these steps for the rest of the rows. Row 1 is type FE. Rows 2 and 3 are type AL. Row 4 is type FE, and row 5 is type O. Now for the coordinates. Rows 1 and 2 should have 0 for their x, y, and z values. For the third and fourth rows, change the coordinates for x to 0.375, 0 for y, and for z, 0.25. For the last row, row 5 with type O, change the coordinates to negative 0.03 for x, 0.05 for y, and 0.15 for z. You can now do your first refinement on this problem. To do this, at the top of the window, go to Calculate and Refine. A file dialog will ask you for the name of this project. You can also change the directory if you wish. We use the name YAG. The current project will be saved as yag.gpx. After this, the refinement will be performed. Click OK to load the results. By default, only the histogram scale factor, which is found under Sample Parameters, and 3 background coefficients are refined. The resulting powder patterns shows a pretty poor fit for a RWP around 34%. The details can be found in the yag.lst file. What appears to be an error includes some structural features which may be from site fractions for the FE-AL sites. The error may also be something about the peak positions, and that may be from a lattice parameter. We can introduce all of these parameters now. Go to the Garnet phase, and then in the General tab, check the Refine Unit Cell box. Next, go to Constraints, located in the main area of the GSAS2 data tree. You will see an empty window with 3 tabs. Click on the Phase tab. At the top of the window, go to Edit Constraints, Add Equivalents. Select AU ISO 1 for FE2 and press OK. A new window will appear. Select AU ISO 2 for AL3 and then press OK. That will form the first equivalence you need between the iron and aluminum atoms that occupy the atom site at 000 in the cell. Repeat this process for another constraint. Go to Edit Constraints and Add Equivalents. Then select AU ISO 3 for AL4 and press OK. In the new pop-up window, select AU ISO 4 for FE5 and click OK. At the top of the window, select Edit Constraints, Add Constraint Equation. A new familiar window will appear. This time, select AFRAC 1 for FE2 and press OK. Again, you will see the same second window. Here, select AFRAC 2 for AL3 and press OK. Do the same thing for another constraint. Select AFRAC 3 for AL4 and press OK. Then select AFRAC 4 for FE5 and press OK. This process set the equivalences and constraints for the 2 iron and aluminum sites in the Garnet. This is done so refinement of FRAC and UISO will succeed. GSAS2 constraints will correct the site fractions and UISO values so that they conform to the constraints as written. You need not be concerned about their starting values beforehand. Also note the way each parameter was named. The general form is P, H, name, num, where P is the phase number, H is the histogram number, and name is the parameter name, and num is the optional number or atom number. Go to the Garnet phase and select the Atoms tab. Note that the FRAC values are unchanged from what you originally entered. Don't worry though, they will be corrected in the next refinement. We now have to set the refinement of FRAC for the iron and aluminum sites. There are many ways to do this. We will show you one method now. First, select row 1 for FE2 and then holding down the Control or Command key, select rows 2, 3, and 4. They will all appear in blue or gray. With the rows selected, at the top of the window, go to Edit Atoms, On Selected Atoms, Refine Selected. In the new pop-up window, select F-Site Fraction. You could select all 3 and GSAS2 would refine FRAC and UISO, but it would not refine the coordinates because they are fixed as a special position in this case. The Atoms tab will have an F in the Refine column for each of these atoms. You are now ready for your second refinement. At the top of the window, go to Calculate and Refine. There is now a much better fit with the RWP around 16%. Select powdergarnet.raw from the data tree and click on the plot window to see the powder pattern. There appears to be some differences in the peak intensities and an interesting offset at the low end of the pattern. To add the remaining atom parameters, go to the Garnet phase and select the Atoms tab. Notice that the frac values for the iron and aluminum atoms now conform to the constraints. For each atom, double-click on the Refine box. A pull-down list will appear. Select U for the yttrium atom, Fu for the iron and aluminum atoms, and Xu for the oxygen atom. Now you can do your third refinement. At the top, select Calculate and Refine. The resulting fit is with the RWP around 10%. There is still an apparent peak offset at the ends of the pattern and perhaps some misfit at the peak widths. This is determined by the U, V, and W parameters found in the powder-garnet.raw instrument parameters window. Go to the instrument parameters for this powder data and select the refine flags for U, V, and W. Next, go to the sample parameters in the data tree. Notice that the histogram scale factor is already being refined. Now, refine both sample X displacement and sample Y displacement. Enter 650 for the goniometer radius. Now, do another refinement. Go to Calculate and Refine. The fit here is nearly perfect, with the RWP around 5%. Under the data tree, click on Covariance. Then go to the Plot window and click on the Covariance tab, and there is a useful display to examine. This is a graphical rendering of the variance-covariance matrix from the last refinement. This matrix is symmetric about the diagonal. Moving your cursor about it will display parameter names, values, and ESDs on the diagonal and the covariance between a pair of parameters off the diagonal. Intense red or green indicates high covariance, green for plus and red for minus, and yellow is for close to zero covariance. High covariances naturally occur for profile coefficients and for background parameters. If during the course of one of your refinements you see white bands in this display, that is the signature of some singularities in your refinement. The offending parameter or parameters should not be refined independently. Perhaps a constraint or equivalence is needed. This concludes the tutorial for neutron CW powder data, yttrium iron, and aluminum garnet.